Hello.
Hey guys.
So this is Rebecca.
Nice to meet you.
So who are you, Rebecca? So what are you doing in my video?
So I'm a physics tutor at Orgo Made Easy / Physics Made Easy.
Yeah, and today we're going to be showing you guys, we're going to be doing the first official Physics Made Easy video. And what topic are we going to be talking about?
So today we'll talk about centripetal force and acceleration.
Yeah, so I'll let Rebecca take it from here.
Okay, thanks, Reed. So for today's problem on centripetal force and acceleration, we adapted a problem from your homework from WebAssign, just so we could explain it and go through it in depth. So we've got our cone, we have a sugar cube inside the cone that's rotating. And our first question that we want to figure out is what force causes that sugar cube to move in a circle? So what I want you guys to do is go back to that slide we showed you and look at the 6 options that we have. So go ahead, go make a guess, and then we'll talk about how to solve this problem. So you may have said that the horizontal component of the normal force is what keeps the cube moving in a circle. If you said that, you were right. So let's figure out why. So to go through this, we're going to do a free body diagram, which I'm sure you guys love. So one thing we need on our free body diagram is we need the weight. So I'm just going to draw that straight down. mg equals weight. And our second force that we'll have on here is the normal force. So we have the sugar cube and the cone. That's creating our contact surface. And the normal force will always be perpendicular to that surface of contact. So we'll get the normal force right here, Fn. So in order to figure out what is keeping that cube moving in a circle, we need to have some type of force that will go towards the center of the circle. So I'm going to break down the normal force into the x and y components, and then we'll be able to see which one is keeping that cube in the circle. So this is the x component of our normal force. I'm going to call it Fnx, and this is our y component, Fny. So I just made the free body diagram a little bit bigger so we can see how to break down the components exactly. So here we're going to draw the x component, and I'm going to call that Fnx. And here we'll draw the y component of the normal force, and that's going to be Fny. So as you can see, the Fnx component, that's what is going towards the circle, so that's what's going to keep the sugar cube going in a circle. So you may have thought that it would be easier to break up the weight or gravity. Let me show you what that looks like if we do that. So if we break up gravity, we're going to get something like this. And if you look at those component forces, you can see that there's nothing that's pointing towards the center of the circle. And that also, it doesn't really fit with our coordinate diagram that we have, because we want a horizontal and vertical coordinate diagram. And these components, they don't really fit into that, so that won't help us solve the problem. So now to think about it a little bit more, what I want you guys to do is to stop the video and draw out a bird's eye view of the cone. So a bird's eye view up here looking down, and then we'll talk about that. Okay, so hopefully you drew something sort of like this. So what I did is I drew in the horizontal component of the normal force towards the center of the circle, like we said. That's our force that's keeping the cube moving in a circle. And what I also drew is the velocity. So the velocity will always be at a right angle to that centripetal force. And so you might be asking, why is there an acceleration? We know velocity is constant in the speed is constant in the x direction. But because velocity is a vector, the direction is very important. And acceleration is also a vector. So the reason we have acceleration is because as the cube moves around this circle, the velocity will constantly be changing directions. So that gives us our acceleration. And this sort of explains it. So the acceleration causes the velocity to change direction, even though the speed is constant. So the magnitude of the velocity will be constant throughout the circle, but the direction is constantly changing as the cube moves around the circle. And that's why we have acceleration in the x direction. So in conclusion, the answer to the first question is the horizontal component of the normal force. Okay, so great job with part 1. Now we're going to move on to part 2. So in part 2, we want to calculate the value of the normal force. So the normal force here, we broke it down into the x and the y components, and that's going to help us solve for the value of the normal force. So one reason we can do this is because there's no acceleration in the y direction. So this sugar cube here, it's just moving around the cone at a constant height. So therefore, when we sum up the y direction components, we'll be able to set that to 0 because there's no acceleration in the y direction. So now I'll show you how to sum up the y component. So we take the sum of the forces in the y direction. And so we have Fny going up. So that will be positive. And then we subtract mg from that. And that equals mass times acceleration. But like we said, there's no acceleration in the y direction. So this will actually equal 0. So then we can say that Fny equals mg. So now Frank is going to take over and show you something that he did that was incorrect when he broke down the mg into the y and x components. So he's going to explain that.
All right, I'm back. So the mistake I made, and some of you might have made, was when we already did a lot of problems with boxes on inclines. And we did that, we often broke up mg into its x and y components when we used this axes. Now, the problem with that is it doesn't work for this problem. So why doesn't it work? Well, it took me like so many days to figure this out, and Rebecca is actually the reason why I figured this out. But let's see. When we did those problems, the box was just sitting on an incline and it wasn't moving, or yeah, it wasn't really moving. There was no centripetal motion. So if we did that, and we probably did sum of the forces in the y direction is equal to Fn minus mgy, because it's pointing opposite it, is equal to may. And then we set a is equal to 0, because our box is just sitting on the incline. It's not moving in that direction. So then you can set Fn is equal to mgy by plus adding mgy over. Also, you've probably seen mgy shown as mg cosine theta after you break down the component with the theta angle and all that. But this is not true anymore. Why is this not true? Well, we know that there's a acceleration towards the center of the cone because the block is moving in a circle. And this isn't true anymore because Fny is definitely stronger than mgy. Or sorry, not Fny. Fn is stronger than mgy. And it's because Fn has a component to it that's accelerating the block this way. All right, so anyways, all right, let me regroup for a second. So this axis doesn't work anymore because what directions are acceleration? Purely horizontal, like that. So this axis is perfect. But if you use this axis, it doesn't work because both of these forces, or all your forces in this axis, there's a component of their acceleration in this direction, in the horizontal direction. Or that horizontal acceleration there's a component of it in both of them. So you can't set your acceleration to 0 for if you analyze the y direction or the x direction, if you set this as your axis. So this is not true anymore. It's not equal to 0. Fn is actually equal to mgy plus may. And we have no idea what that is, so you can't do this problem if you use this axis. Cool. Make sense?
Yeah.
All right, awesome. All right, so now...
You can do the angle thing, right?
Yeah, exactly. Okay, so now back to the correct way to do it. You use this axis, like Rebecca said, Fny is equal to mg down in this axis, and we know acceleration is 0 in this direction. Because the acceleration is purely in the x direction. Now, Fny is not what we're looking for. We're looking for Fn. So she's going to have to somehow relate Fny, the vertical component, to Fn. But in order to do that, she has to use this angle, or somehow bring this angle into this triangle. So I'm going to show you guys how that angle gets in there. So first we have to think about this triangle right here. I'll do it over here. Force normal is here. This is our vertical line leading to the bottom. This is the incline. This is theta 1, or theta. And so we have a right triangle right here, actually. This is a right, not a right triangle, yeah, right triangle. You have a right angle right here. And so if this is theta, which is, in the problem, what's the angle? 34 degrees. Okay, so this is 34 degrees, this is 90, and we're in a triangle, and the total angle has to sum up to 180. Then 180 minus 90 is 90. 90 minus 34 is what? 56. Okay, and now our Fn has its x component here, Fnx, and its y component here, Fny. Well, here's another right triangle. Boom. 180 minus 90 is 90. 90 minus 56 is 34. So our theta actually is here. I'm going to draw it here. Boom. And boom. Okay. Hope that made sense. If not, just ask us in the questions down below, and we'll be happy to answer you guys. All right, so I'm going to give it back to Rebecca, and she's going to finish up this problem for you guys. Okay? See you in a bit, or if not at all.
Okay, so thanks for that explanation, Frank. Now we're just going to erase this part because it's all incorrect. So,
work is gone.
So Frank showed you how to get the angle. So now that we have this angle here, we can use trigonometry to figure out how to get the Fny. So because Fny is opposite theta, we're going to use sine. So we have the sine of theta is opposite over hypotenuse. And specifically for this situation, it's going to be Fny over Fn. Fny over Fn. So for this problem, we want to be able to plug Fn and the sine into Fny. So we're going to move Fn to this side. So what we end up with is Fn sine theta equals Fny. Awesome. So now we can plug this in here. So we have Fn sine of theta equals mg. And because we're looking for the normal force in this problem, we want to isolate the normal force on the left side. So we'll divide by sine theta. So we're almost at the time where we can plug in numbers. We have one last thing to do. So in the problem, it says that the mass is 550 grams. But in order to solve this problem, so all the units cancel, we need the mass to be in kilograms. So we're going to do a little bit of dimensional analysis up here. So mass equals 550 grams. Then we'll multiply by 1 kilogram divided by 1,000 grams. And what we get is 0.550 kilograms. Awesome. So now we can go back. We can figure out what our value for g is, which the problem told us would be 10 meters per second squared. And then we can just plug it in. So the mass is equal to 0.550 kilograms. Multiply that by 10 meters per second squared. And then we'll divide by the sine of 34. So when we plug all those numbers into a calculator, we get 9.84 newtons. So the value of our normal force, this total normal force here, is going to be 9.84 newtons. And make sure that you use degrees. You have your calculator set to degrees, not radians. So great job with part 2. We're going to move on to part 3, which is calculating the velocity of the cube. So, I lost myself. Always.
Always happens.
Always. I look at it and I'm like, what?
No idea.
Okay, I was going to explain why centripetal acceleration. Okay. So, great job with part 2. We're going to move on to part 3, which is calculating the velocity of the cube. So, the way we can do that is by using the horizontal component of the normal force. So, we said before that we only have acceleration in the horizontal component of the normal force in that direction. So, one thing that we also know is that for centripetal acceleration, the acceleration will be equal to v squared divided by the radius of the path that the cube travels in. So luckily the problem gives us the radius, and all we need to do is solve for the velocity. So we're going to do the same thing here, but in the x direction. So we'll sum up the forces in the x direction to get our equation. So we have the sum of the forces in the x direction equals the horizontal component of the normal force, which is equal to mass times acceleration. And like we said, this acceleration will be equal to v squared over r. So we'll set that equal to mv squared over r. So like we did before with the y component, we also have to set the x component equal to something relating that to the triangle. So in this case, we used sine because it was opposite over hypotenuse, but the x component is adjacent to the angle, so we'll use cosine here. So we have cosine of the theta equals adjacent over hypotenuse, which is equal to fn x over fn. Then we'll move that over, and fn x equals fn cos theta. Okay, so now we can plug in fn cos theta to here. So we have fn cos theta equals mv squared over r. And in this case, we're looking for the velocity, so we want to isolate the velocity on this side. So we'll do a little bit of rearranging. So we'll multiply by r. Now we have r fn cos theta. We'll divide by m. That equals v squared. And then all we have to do is square root it. So we'll square root it like this, cross out that, and now we have our equation. So one last thing we have to do before plugging it in is for r, we have to convert that from centimeters to meters, just like here we converted from grams to kilograms, because that way all the units will cancel. So r is equal to 20 centimeters, then we multiply by this, 100 centimeters for 1 meter, and we get 0.2 meters. So now we're ready to plug and chug, and we'll have our final answer. So r equals 0.2 meters. For fn, we can plug in 9.84, which we got in part B. So 9.84, multiply by cosine of 34, and then divide by the mass, which was 0.550 kilograms. And remember, for cosine, we want that to be in degrees, not radians. So after we set this equal to that, we'll get our final answer of 1.72 meters per second. So velocity equals 1.72 meters per second. And there you have it.
And that's the velocity in, what velocity? Velocity is moving in a circle. Alright guys, so that's centripetal force / acceleration. Made easy. Hope you guys liked it. That's how we think about these type of problems. If you have any questions, feel free to ask us down below in the comments.
If you have any feedback about the video, please let us know, because this is our first Physics Made Easy video. We are open to suggestions on how to improve in the future.
Exactly, yeah. I usually do orgo videos, so this is like a new element for me. So, yeah. And if you ever need, if you're looking for tutoring, Rebecca does Skype tutoring and in-person tutoring as well, depending on the time.
Yep.
And I also do tutoring as well. If you're watching this video not in 2016, like way later, we'll probably still be doing tutoring.
Probably.
So, yeah. All right, cool. Thanks for watching. If you like this video, make sure you like it down there, wherever the button is. Hit subscribe if you want to keep being updated when we make new videos. We'll probably be making a few more this semester. Yeah. And maybe a few more next semester for 106.
Yeah. Good luck.
All right. Bye.
Bye.
Bloops. Okay, just so there's an audio spike and you can synchronize it better.
Got it.
Cool. So, yeah, I guess you can hold it. So, ready?
Yeah. Should we redo that? Yes.
Yeah.
Right now.
That was okay. Was that kind of wordy towards the...
Oh, I feel like we should redo that.
Okay, sure, we can do it one more time.
Okay.
That's it. Okay. Video is going.
Should I do the clap thing?
Yeah. Record.
Got it. Recording.
Recording. All right. Synchronized clap.
3, 2, 1. That's fun. Okay, so great job with part 1. Now we're going to move on to part 2. So in part 2, we want to calculate, and to do that, we're going to use the components y and x of the normal force that we calculated before. Oh. What was I going to do next? I already forgot. I'm sorry. Keep going. We'll cut it out later. Okay. So great job with part 2. We're going to move on to part 3, which is calculating the velocity of the cube. So, ooh, I lost myself. Always.
Always happens.
Always. I look at it and I'm like, what?
No idea.
Okay, I was going to explain.
Okay, synchronized clap in 3, 2, 1.
All right. So, yeah.
Let us know now.
Alright.
Alright.
It is recording.
Your favorite part?
3, 2, 1. Okay, I need a marker. Okay, so thanks for that explanation, Frank.
Yes. Alright. Go. Yeah, and just keep it like relatively higher this time. Synchronized clap in 3, 2, 1. Okay, wanna do it together?
No.
No, okay, fine. Bye. Gosh. Anyways,